Okay, good.
Professor Guendelman. Yes. Okay, the title of the talk is shown here. Please proceed.
Yeah, you can see my slides. Okay.
Yes, yes.
Okay, so I'm going to tell you about dynamical tension strings, how it relates to a new way to construct brane walls, and the lifetime of the homogeneous and isotropic cosmology. Okay, there's an interesting connection with previous talks, for example, unimodular theory, which plays with the square root of minus g. The square root of minus g is basically the measure of integration, right, in the gravity action. But unimodular theory addresses this question by saying g is 1, right? The dynamic is 1. Another way to address this question is to go to metric independent Riemannian volumes. For example, if you have scalar fields, tensor fields, you can construct a density out of a contracting epsilon 1, mu 1, mu 2, up to mu d with the curl of this antisymmetric tensor. And this is a density which it behaves exactly as a square root of minus g, and it can be used as a measure of integration. One particular way to define a metric independent measure as opposed to square root of minus g is by means of four scalar fields if you are in 4 dimensions. Interestingly, in another talk before, we had this 4 scalar fields in 4 dimensions used to help in building graviton mass. We are not going to do that, yeah, but still we're going to use the 4 scalar fields in 4 dimensions, or 2 scalar fields in the string theory, for example, concerns the worksheet of the string. Then if you multiply phi with the d4x, this phi transforms according to the inverse of the Jacobian, and this ddx according to the Jacobian. I would like to address, for example, work by Pirogov, where he used 4 scalar fields in gravity in a more general point of view, not just use it in the measure as I'm using this point. And as you have seen also before, it has been used in the construction of massive gravity theory. So we use these 2 scalar fields in gravity, or in a string theory, or 4 scalar fields in gravity. Yeah. And we have done a lot of work in gravity, for example, right? In gravity, this actually produce, for example, kind of are related to you get some integration constants that are relating to floating cosmological constant, or these integration constants can change the potentials. And a particular version of this, it gives actually unimodular theory, but in a covariant way. And now, but this is not the topic of this talk. The topic is not gravity, it's string theory. So what are we going to do? We are going to modify the string theory. The string theory is in the Cosmological formulation. We write the square root of minus gamma EB. And this x mu is the embedding coordinates. Gamma EB is the intrinsic Riemannian metric on the 2-dimensional worksheet. Gamma is the determinant of gamma EB. G mu nu is the embedding space-time metric, and T is a string tension. The equation of motion is the energy momentum tensor is 0. energy momentum tensor in the worksheet, varying with respect to gamma AB. And the analogous of the geodesic equation is this, right? Now we want to replace square root of minus g by density, which is metric independent. A consistent way to do that is to replace the where is the square root of minus gamma there by this density, but then you have to add this term where FAB is a field strength that lives in the string. Yeah, FAB is a dA AB minus dB AA, right? And this is consistent theory, and it has a conformal invariance. Gamma AB goes to some function J, gamma AB. This function, J is also the Jacobian of transformation of scalar fields. So phi goes to Jacobian, and this is also under this scale generalization of conformal invariance. The equation of motion with respect to the variation of the scalar fields is a matrix times the Lagrangian here. This matrix here, this matrix times the derivative, contracted with the derivative, okay, at axial Lagrange. If this derivative, the matrix here, it has determinant non-zero, which is the determinant is basically the measure back, right? You are forced to have this Lagrangian equals to a constant. The variation with respect to gamma AB gives you this equation. From the contraction of this equation, you can replace here this object here, and then you are forced to have m equals 0. So then you can solve this object here, epsilon CD FCD divided square root of minus gamma, and then you get the ordinary Polyakov action, Polyakov equations. The most interesting equation, however, most interesting in the sense that is the new feature of the theory, is the variation of the gauge fields. Gives you this equation. It gives you that the ratio of these two measures is a constant, and this constant, from here you can solve the square root of minus the measure and you put it back into the action, and then you identify this T as the string tension. The string tension is derived as an integration constant. The integration constant is a property of the worksheet, so any other string can obtain another tension. So you may have a multi-tension, and you can formulate the theory of brains also is similar story. You have dynamical brain theory, dynamical brain tension theory. So I'll read just the title because we are short of time. Each string or each brain in its own worksheet determines its own tension. Okay. Okay. We're going to put the background fields now because the theory, according to Schwinger, for example, you understand the theory when you put the background fields, right? And this is the philosophy of string theory also. You put all kinds of background fields. And you can start by proving putting a coupling, the field A coupled to a source. Then the tension will not be a constant because the equation now is changing to this, right? This source here. How do you derive a nice source? You put the background field, which is a bulk field that we call it the tension field. And this field phi mu induces a current, right? you have the derivative of the current and you project it onto the worksheet, right? And you take, you have the derivative. When you put this back into here, you can see that you can integrate such an equation. The tension now is not this, right? But is E phi plus integration constant. This integration constant can be different for each string. So there could be many strings with the same integration constant, another set of strings with another integration constant, and phi is a square root of minus g times E phi plus t. Okay. Now we consider a particular string, for example, a particular string has this coupling here, right? And we put also, as in the ordinary string theory, antisymmetric tensor field and a dilaton field. But to simplify matters, we take this well-known stuff as trivial. For example, this antisymmetric tensor field pure gauge, this dilaton field a constant. And we see that the role of the metric now is this conformally related metric, Gi mu nu equals this factor times G mu nu, where G mu nu is the embedding metric. But if I were to quantize the theory and impose that the beta function is 0, the one that will satisfy the Einstein equation is not the embedding metric, is rather this metric. And if I have two types of strings, there will be two types of metric that will satisfy the Einstein equation, and they will be conformally related, right? I'll pass this, right? Two metrics, for example, we have two types of strings where two integration constants are different. This metric here and this metric here both satisfy the Einstein equation, and they are conformally related because both are conformally related to this embedding metric. But notice this is very non-trivial because the Einstein equations are not conformally invariant. So if you consider these two equations, it's a non-trivial equation for this new field. For example, you call this conformal factor C. You have this. From this equation, you can solve for the field, and then you can solve for the two metrics. This C is physical because both metrics, they can be, for example, both flat or whatever. But we are not allowed to bring both metrics to the Minkowski form at the same time. We cannot do that because we can only do for one. And you can see that it's physical, for example, by considering the ratio of the square root of minus G1 divided by square root of minus G2, which is a scalar, and is C to D to the minus 2. So this constant here is physical, even if the two metrics are related by a coordinate transformation. Okay, this is written in a more clear way. These two metrics, for example, you take two flat metrics, cannot be transformed simultaneously to Minkowski space in standard coordinates, right? Out of these two flat metrics, for example, you can construct the true tensor, for example, the difference of the Levi-Civita connections. I'm going to go fast, but for the simple examples because we have little time. We have, for example, flat space in the Milnor representation, which you can bring into, you can generalize to the dimensions, right? This is a hyperbolic space, right? If you do the transformation, T goes into 1 over T, you get a conformally related metric to this. You can multiply by another constant. So you got the value of C, right? And then you can solve for the two metrics, right? And then you can solve for the metric 2, the metric 1, the embedding metric, right? And you can play around with the negative, one tension negative, one tension positive, and then you get non-singular solutions. Okay, you can work with the warp spaces like Wesson, right? You have a common factor elsewhere, everywhere. This is flat space, but Wesson was smart enough so that the slices L equals constant look like the zeta space. Okay. And then you can play with the even more general solution, Schwarzschild de Sitter space, right? Which are solution of Einstein equations, right? The flat space, empty space. So you can again do the L goes to L equals inverse, L inverse, right? And then you get the two related equation. Okay. But we have little time. Yeah. We do the case where the two metrics are related by a constant omega square is positive, and these are the equations that relate the two tensions. This is the one tension and this is the other tension, and you can solve. And you can find points in space where the tensions goes to infinity. Okay. Okay. This is okay. At the points the tension goes to infinity gives you the idea that the Hagedorn temperature is infinite. That means that there is no Hagedorn temperature, no limit in temperature. Okay, that's one idea. This is repeating again this feature, but I want to go to the, I told you, brane walls. Brane walls is the most interesting feature. Let us consider Minkowski space and Minkowski space after a conformal transformation. This is the transformation, right? It's actually people discuss that it's wrong to think this as a conformal as a coordinate transformation because it changes the topology. This does all kind of stuff. But okay, it doesn't matter. We have two conformally related metrics. The metric 2 related to the metric 1 by this conformal factor. A mu is a vector, right? A mu is a vector that can be light-like or it can be not light-like, that means space-like or time-like, right? These are the notation. A square is a mu, x square is x mu. We look at our omega square, right? It's like this. We consider first time-like, light-like. So it's A, 0, 0. And we solve for the tensions. The tensions are of one string. One type of string is this. The tension of the other string is this. Look at the points where there is a points t minus x equals 0. Produces infinite tension, and also for the other string. And the point where this is 0 is another place where the tensions go to 0. These two places, these two surfaces go with the speed of light, and between them, the strings are constrained because the tension between these 2 points is positive. So this is like you are generating a brane, only that is a brane that's moved with the speed of light, something like this. We call this light segment compactification. Now, if you want to do generation of another kind of brane, which is not light. So you just take a square non-zero, which can be time-like or space-like. Both give you a generation of branes. The string tensions in this case are these divided by these two denominators. For both branes, for those strings, the branes are the limits where the string can live are this surface and this surface. At this point, the tensions become infinite. So the tensions are, the strings are bounded by this. And let's look at this. What are these? For example, for A mu is time-like. Take it A equals 0, 0, 0, 0, and then you see that the two surfaces are this, right? Like and this. This is like an hyperbolic motion, right? And this is an interior boundary that doesn't exist for all time, but at some times it starts to exist, okay? And between these two, between at asymptotic times, the distance between these two surfaces that where the strings have infinite tension, and therefore the strings are constrained into between these two surfaces, moves, and the distance becomes smaller and smaller. You can do the same, similar effect happens if A mu is space-like. You have two surfaces, and again, one is external hyperbola, the other is internal, and the distance between the two becomes very, very small. So you are generating a brane world scenario that differs very much from every brane world scenario that has been investigated before. I analyze a problem here that I will not have time to discuss. As you say that if you have infinite tension, I just say what it is. You have infinite tension. Does it bother you with the back reaction of this large string tension if you put it on the boundaries? And the reason, the answer is no, because if you mash two spacetimes or almost flat spacetimes in a wormhole form with a wormhole structure, you can have two flat space match without problem. So I go through this just to tell you that this analysis exists. Now I go to another subject. Phenomenological advantages of these brane world scenarios over traditional one. There are very serious problems with the large extra dimensions. Here we will not have large extra dimension because the dimension becomes the dimensions become very small between the brane, right? It's like the extra dimension of the right. The problem becomes because of the observation of the merger of neutron stars. Doesn't see any difference between the propagation of gravitational and electromagnetic waves. This is a paper of this. That would be predicted by, for example, Randall syndrome 2, for example, right? Which is one brane, right? And the gravity can propagate to the bulk, right? This is experiment of two neutron stars merging. Yeah, you see. If you are in flat space, you have 1 over r squared, 1 over d squared intensity decaying, right? If you have the traditional brane world scenario, you put the brane here, right? And the gauge fields live on the brane. So this includes the photons, right? While the gravity lives on the bulk, right? The brane, the light will go like 1 over d minus 1, right? On some scales, the gravity also does the same thing, but on other scales, the gravity extends to the bulk, to the extra dimensions, right? But this paper says that this is very constrained. You don't see any effect, any difference between the intensity of the gravity and the gauge, the gravity and the gauge fields. You say D equals 4. There is no asymmetry on propagation of gravity as compared to light. In the brane worlds with extra dimension is disproved. This is, for example, Randall syndrome 2. The Randall syndrome 1 with the 2 branes is okay, but the one of the brane, recall, is negative. So this is a kind of, from theoretical point of view, is a little bit weak. In our case, both branes are positive, and we are free from this problem because we confine everything, both gravity that arises from closed strings, right? I should have said the tension goes to infinity, doesn't care if it's closed string, open string, is a universal effect. So universally, everything is constrained to between these two surfaces, right? We could have a combination of the ordinary brane world scenario and dynamical string tension, yeah, but okay, this is some embellishment. And I want to go into the last subject, life of the homogeneous and isotropic universe. As I told you, we have this equation for one tension and the equation for another tension, right? We can take the limit. An interesting limit is that when A goes to 0, this constant A goes to 0 here in the conformal transformation, in the special conformal transformation, and we take the T2 minus T1. You see that there is, if you take these two guys go to 0, but such the ratio is constant, you get that the tension of the one string is equal to the tension of the other strings, goes like K to 1 over T. And you don't get the brane world. In this limit, you just get the homogeneous and the isotropic universe. Now, if you consider that A is finite and T2 minus T1 is small but finite, you will recover the brane world in a time delta T given by this equation. So this is a kind of uncertainty relation, so that tells you how long homogeneous isotropic universe dynamical string tension until it turns into you go back to the exact equation without negating anything, and then you go back to the brane world, right? This one surface is like that, the other surface like that, and the distance between the two surfaces is like this and goes to 0, so you get the brane world. So this gives you the lifetime of the homogeneous and isotropic universe, right? Where the homogeneous and isotropic universe starts and then becomes a brane world scenario. Okay, you can think perhaps that this delta T comes from quantum fluctuations, and if you think in this way, then as the brane world is generated, these different components, entangled components of these two serial strings, decohere, and then you will get okay, some references, right? You can see these are some references that relate to application of measures in gravity. Then we started working on modify measures applied to strings, right, and branes. And then introducing these tension fields, we have this. We have a essay that won an honorable prize. We have a paper in European Journal of Physics, European Physics Journal last year. We have this brane world creation in dynamical string theory, the dynamical string tension theories. And the life of the homogeneous anisotropics is like was published months ago in the European Physics Journal. And Thank you very much for your attention.
Thank you very much. Questions from Zoom first. Well, no questions from Zoom, from the audience. Hi, Eduardo. It's Alexander Zakharov is speaking. It's nice to hear you here.
Thank you. Yes.
I have a question about this proposal from a group of people to discover some leakage of gravitational wave energy from mergers of neutron stars. So it's a very nice idea, but I would like to ask you, why did these people consider namely neutron stars, not black holes? Because
yes. Neutron star. This is a very good question, because neutron stars will give you both light and gravity wave.
Yes, but there is no leakage in electromagnetic waves, as you mentioned.
Yeah, because according to the Brainwell scenario of string theory, right? The traditional string theory, the gauge fields live on the brain. They don't escape the brain. There is a brain, and then Randall Sundrum said that okay, we do this is for the brain, but the gravity is wrapped, but it can extend to the another dimension, right? Or several other dimensions.
Question: why do you need electromagnetic radiation in this event? For instance, if you have a binary black hole mergers, you have only gravitational waves, and if you
but this is for black hole mergers. Black hole mergers, you have only gravitational wave. That's true. But if you have a neutron star merger, you produce also electromagnetic. So then you can compare. A lot of modified gravity theories have been excluded mostly from the neutron star merger, not from the black hole mergers, because they give you this process gives you the possibility of comparing light with gravity, and then they say gravity moves with the speed of light, or gravity intensity of gravity decays like light, and everything's like light for gravity.
Okay, so, except
gravitation. But you must have neutron star mergers to compare, because if you have just gravity, you measure gravity, but you don't compare with light. Yeah.
But yes, but the scenario for electromagnetic radiation for neutron star mergers is very poorly understood. You know.
Okay. I am citing this paper. Let's see. To tell you the truth, I haven't gone to all the details of this paper. Yeah, but they claim they did it. Okay, this guy David Spergel is supposed to know something. I don't know.
I believe you. But the last question. So, what about other astronomical ways to find signatures of extra dimensions or brains, except gravitational waves?
Yeah. This I don't know. Yeah, I have to. This is the one that has been discussed more, right? But yeah, it's kind of a negative. Yeah, but.
Okay, thank you very much. Good news is that we have nearly recovered the schedule. Our last talk on big gravity by Professor Solovyov